received his PhD from Philips University in Marburg.
Correct.
He's making work at Darmstadt, Germany, the University of Brussels, and the Fieldwork University in Edinburgh, United Kingdom. He joined us in 2009, years ago, and his work has focused mostly on analytical and experimental work on nonlinear photonics, and particularly emission properties and dynamics of modern photonic sources, coupled laser systems, networks of lasers, the use of chaos for the encryption of signals, a very interesting work which is not the topic of today, because here we can also another very interesting topic he's working on, which is this neuro-inspired optical.
Such a big audience at the end of 2 weeks. I know it has been quite demanding for you. So as a topic and title of my presentation, I have chosen Neuro-inspired optical information processing concepts and applications, but I might as well have chosen other titles. I might have chosen optical machine learning implementations for information processing, or I might have chosen complex systems-based optical information processing concepts and applications, or simply how to teach a laser to compute. So why do I address all these different titles? It is to illustrate that what I'm going to discuss with you in the following is quite multidisciplinary of fields, and therefore at some points it might sometimes be a bit unfamiliar for you. So in that case, please interrupt me at any time. So if I introduce it from the viewpoint of complex systems, since this is a summer school on statistical physics of complex systems, I very much like to introduce information processing employing complex systems using a quote from some of the pioneers actually in complex system science, Jim Crutchfield, Bill Ditto, and Sudesh Narasimha, and they, in a foreword already several years ago, meanwhile, to a focus issue, they wrote about analog, so a kind of unusual computing, analog intrinsic computing implementations. The technological promise of intrinsic computation is substantial. Faster, less expensive, and more energy efficient in the natural world. And moreover, how does utility factor into the fundamental physical limits of computation? Constructive answers could well break the prevailing digital technology lock-in and, as a byproduct, enrich the science of information age. So let's see how much of that very full-mouthed promises we can already keep and what really of that might have prospects for the future. So my plan for the course today, or for the seminar today, is to convey in the end 3 messages to you, 3 key messages. First of all, following this multidisciplinary perspective that I'm going to introduce, I would like to show you that this gives rise to novel insights and understanding of information processing in general. Second, by implementing multidisciplinary concepts, I will show you that you may question and overthrow aspects considered usually common in photonics, that can lead to an ultra-fast and efficient computer for certain tasks. Ultimately, I will show you that using these 2 simple things, these 2 simple components from telecommunication, a semiconductor laser and a piece of standard optical communication fiber, you can build a computer that certain tasks, or for certain tasks, can be so efficient that it's 10 to the 5 times faster than a standard PC that maybe some of you might just be reading your email on, and also 2 to 3 orders of magnitude more efficient in terms of energy consumption. So all this is in the philosophy of what I like very much, the quote of Richard Feynman: "What I cannot create, I do not understand." So what's wrong with digital computing? So why do I talk about analog computing here? About 70 years, we have digital computers evolving at an immense pace and actually always following the same, more or less, architecture that was introduced by John von Neumann, Zuse, and Alan Turing. And actually the big success of this computing relies on what is known as Moore's law, which is that every 2 years, more or less, the number of transistors in integrated circuits doubles, or in the end, the performance doubles even every 1.5 years. And this shows Moore's law up to now. However, there's problems with Moore's laws, which have several reasons. Certainly one of it being that the miniaturization has limits. And by many experts, it is assumed that we will definitely run into problems latest around 2025. But there's not even the communication between computers. Already in 2016, more or less 5% of the total US power consumption was consumed only from computing. And if you then see how much the demands for information processing is growing, then you can make a simple estimation. And that is what some people did here in this benchmark. And if you extrapolate the amount of energy required for computation, even considering the increase in energy efficiency typically in computer chips, and you compare it to the world's energy production, then latest by 2035, the energy required for computation will become larger than the global energy production. So there is a big problem. So we need significant improvements in energy efficiency and certainly new ideas in computing. There are indeed actually a lot of interesting new ideas in computing, and it's actually that I would say we're experiencing of machine learning, like AlphaGo beating the best Go player in the world, Neuro-inspired hardware, where you really try to mimic every single neuron and every single synapse in the brain by computer hardware, or the promises of quantum computing, or a lot of other concepts, including swarm intelligence, if you think of complex systems, specialized solutions like coherent Ising machines, or DNA computing from biology. So why yet another approach? Well, because we think that if you do not concentrate only on a single field, but really try to take knowledge from different areas, and that's why we're here in an interdisciplinary institute, if you take input from machine learning, neural information processing, complex dynamical system and complex networks, and photonic systems, you end up, at least in our case, in first approximation, by what we call delay-based photonic reservoir computing. And I would like to explain to you in the following what we mean with that. So first of all, I would already, before introducing it, give you an idea why we chose this approach and what we think are the advantages of this approach. By choosing reservoir computing that I'm going to introduce in a minute, we choose a concept which is particularly interesting for its simplicity and power and for its easy training. It has inherent memory, therefore being able to process sequential information like we can do when we listen to language. It's particularly suited for hardware implementation because of the simplicity of the concept. So we use photonics because photonics promises us a lot of advantages in terms of speed, parallelism, nonlinearities. We already use all the names, and we will see that this will lead to an extreme hardware efficiency. And finally, the philosophy behind our approach is a minimal approach, a bottom-up approach. Not like realizing, like with True North chip or brain scales, realizing a chip which has all the neurons and synapses in the brain at once, but where we say we want to fundamentally understand information processing and get more insight also in dynamical phenomena understood as intrinsic computing processes. So what is reservoir computing and how does it work? Well, I start with a statement, since we're here in complex systems science. I would like to make the statement that actually many complex networks can in principle perform information processing. But how it is, for example, done in reservoir computing is the following. So assume you have a complex network of different neurons or nodes, depending which perspective you choose. And you see this is a recurrent network. Recurrent means we have loops here in the connectivities, which means if we, for example, introduce some information to it, it will remain and propagate for a while within the network. So now we have some information that we would like to process. Yeah? So let's assume, usually in machine learning, you assume you have a random network. And also you assume in machine learning usually that you have a random connectivity from your input information into this complex network. Then the input will create some activity within this network. The information will actually propagate within the network, and when the next information comes in, it will not find the network in its initial state. It will find the network in a state which is defined by the response to the previous information it had received. And that's how it in principle allows for information processing of sequential or contextual information. A very important aspect of it is that contributes to the simplicity of the concept is that you don't actually touch the connectivity of the network. Once you have defined your complex network, you leave it as is. You don't need to change connections or anything. This will be very important for implementations, because if you have to be able in hardware to adapt all the connectivities in a network, that's really a challenge. So the simplicity of this is certainly something which is, that is that we simply add up all the activity of the nodes or neurons in the network, and only by choosing linear weights with which we sum it up in a certain way, by choosing them properly, we can define actually what is called here output nodes, which could give you a response or exactly the response of the calculation you want. Yeah? Only by choosing these weights properly. And as I will show, this kind of training is extremely simple. So this concept is actually not so new. It has been introduced more than 15 years ago, actually independently from two different areas, both from the machine learning side, where it was called echo state networks by Herbert Jäger, and in 2002 by Wolfgang Maas in Coming Right. So what are the conditions for reservoir computing to work? When does it work? What are necessary requirements? First thing we already talked about. We want to be able to process contextual or sequential information, so we need fading memory. Why does it have to be fading? Certainly, if you listen to me now as a speaker, it's relevant for you what has been the previous word in my sentence, but it doesn't matter what, for example, the speaker last week, for example, said at this time. Then we need to be able, if we want to differentiate different classes of, for example, words or patterns, to mention some of the computations we're going to do, you need to be able to separate them, right? That will be one of the tasks we want to do. If I say different words, you want to be able to distinguish the words, and independent of whether I say it or whether you say it. And we need what we call the consistency property, that similar inputs will result in similar outputs. So that means, again, if I say the same word as you say, the response needs to be sufficiently similar that you can categorize it as being the same word. Drive a dynamical system multiple times with the same input, it's not a trivial property that you will always get the same output. So how does this work? How can we, for example, distinguish different classes of input signals, so for example, different words or different patterns? So that is something that the concept has in common with many machine learning concepts. It's based on the following idea. Let's assume as a cartoon, you only have two different symbols you want to distinguish, like here the donuts and the stars. And you would like to do that, for example, here in 2D. You see, as they are placed in a phase space, for example, it will not be easy to separate the two, or the separatrix between the two is a rather complicated function. It might be very complicated to determine it. But if you go in higher dimensions in space, for example, if you have a higher dimensional phase space, it becomes more likely that you might be able actually to linearly separate them. So just having a hyperplane, a linear hyperplane, which is capable of distinguishing, here illustrated by the third dimension, right? So they might differ in the Z variable. But classification is certainly not the only task we can talk about if we talk about different calculations. We can also talk about, for example, what we could do, nonlinear prediction, yeah, as a typical task. If we have a nonlinear time evolution, which is present a dynamical system, how can we train, for example, our system to represent a different dynamical system? And how this works, I took some inspiration from a video game that you may know. It's called Shadowmatics, I think. And what you have to do, excuse me, in this game is you have these kind of three-dimensional objects which look very complicated, and you have to find the right direction and the right orientation of this object such that the shadow gives a certain form, right? So that you can illustrate or imagine to be, for example, the dynamical system or the system that you want to be represented by your system. And this is, for example, what you have to find the right orientation and the angle to project it. That will be the choice of your linear weights, because this is equivalent to a rotation in phase space. So if you, for example, want to do a time series prediction, and I apologize for my poor hand drawing skills, you may start, for example, from a two-dimensional state space with x1 and x2. And then you have to rotate it, and you have to find an orientation of it such that then the linear projection of the points versus time would, for example, give you the next point in the time series, or, for example, another variable of the corresponding dynamical system, right? So that's the idea of it. And there's one aspect that I forgot to mention. The fact that we say we don't train the connections of the network itself, but only the readout, means we can do in principle all kinds of calculation with the same network, because the network is not altered. Only the readout is altered. So we only have to add another readout node, another output node, to do any kind of other calculations with the same response of the same complex network. And I tried to illustrate that as well for you, and I borrowed that image from the book Gödel, Very Different Objects, right? Next point is, if we now really think about implementation, implementing such a complex network, and usually for even normal tasks you need networks of hundreds, if not thousands of these neurons or nodes, is still quite a demanding task. So we thought, what are really the essentials that were defined as necessary conditions for it to work? Remember, that's besides the consistency and the separation property, it was that we were able to map a low-dimensional input signal onto a high-dimensional phase space. So the question is, what is the simplest possible dynamical system that allows us to do that? And those are actually very simple delay dynamical systems. So in the simplest case, it would be defined here as a differential equation that the evolution of x is not only defined by the value of x at the same time t, but also the time t minus tau earlier. And these are quite peculiar dynamical systems. So you have a nonlinear node, and you have a delay loop that the system has distributed along the delay line. So if you want to know the state of the system at any moment in time, you do not only need to know x at time t0, you also need to know the whole memory function, right? Because that will be the next values that will drive your nonlinear node. And all these degrees of freedom can therefore be considered distributed along the delay line. So the state is defined as a continuous function of an interval of duration of length tau. So in the end, you can assume that this would represent more or less a ring network where you have virtual nodes or neurons oriented along here the delay line, separation of which you can choose where you want to tap it. And you take those as the degrees of freedom of your system. But the point is, how can you address them? How can I really use them that it will still be a low-dimensional object, right? So that's why we introduced the following protocol to operate the system. So if you have, for example, a certain data input stream here for simplicity shown as a scalar input, and you see 3 values of the input, we sample and hold them for a duration of one of these delay times, and we input during one delay time one of these input data. This could be a scalar value, but it could also be a vector if you want. And we do now the following. We do what we call masking. We multiply this data with an envelope. Can be a binary envelope, can be actually, meanwhile we know you can multi-value continuous function to mask it, no problem. However, important is that for every of the data that you do it, you take exactly the same envelope. Yeah? And what does this envelope do? This envelope causes that the dynamical responses that are then distributed along delay line are different at any position within the delay line. So if we feed this, for example, in our system with a nonlinear node and the delayed feedback, we will get transient nonlinear responses like that. And all of these points around the delay line will have a different nonlinear response because the sequence is different. And then all you have to do is really take the phase space, which is spanned by all these values along the delay line, and again train your linear coefficients in order to give you your calculation result as necessary. Certainly there is no guarantee this works. In particular, since the concept was introduced, who says this would be working? So how do we train it? Well, the training, as said, is very simple here. And it's really just summarized everything here on this one slide. Assume, for example, you have here in this case 400 neurons in your network, 400 virtual neurons, 400 nodes distributed along the delay line. And here in the vertical direction, so in the columns, you see the dynamical responses for all these different neurons for a signal which varies here in time. So this represents your response of your system to a certain data input. And assume this was, for example, a word I said, the word 5. And you want to recognize this is the word 5. Yeah? And what we're looking for is nothing else than a matrix W multiplied with this response such that it identifies, for example, this word at any moment in time that it was the word 5. Yeah? If you do that with many examples, all you have to do, and then you can, for example, confront your system with someone else who says also the word 5 and see, are you able to recognize the word as well? Can you generalize? And that is, for example, shown here. So you have a before unseen response, and then you multiply it with a matrix W that you have determined by linear regression, and then you get maybe something like this. So it will not be ideal. Yeah? But you get a distribution. And here, for example, the distribution is clearly peaked at, I think it's 8. And then you would decide, okay, this was, for example, the word 8, if the task was that you had different words being spoken which correspond to different digits. It's already important to say this is not the only possible training. So we also tried other kinds of training mechanisms like backpropagation that is popular from deep learning or gradient descent. You can do that as well. But it works pretty well already with a simple linear regression. So indeed, a little bit introduced or implied a bit in my presentation, which is a standard benchmark given by the National Institute of Standard and Technology in the US, which is a database of 10 digits spoken by 5 female speakers, 10 times each. And the task is, okay, how many of those do you recognize correctly? You take a subset of those to train the system, and then the other before unseen samples, for example, to test it and see how well is it capable of recognizing those numbers. And this is the system we are realizing it with. So it looks a little bit complicated. So this is the scheme of the photonic setup, but it's really as simple as I more or less showed in the scheme. You have a semiconductor laser here, so this little object, which is, well, actually this is only the holder. The laser itself is so small you can hardly see it by bare eye. And then this is the fiber loop, right? There's certainly only a few more components in there in order to control the feedback strength, the polarization of the light, to couple out some light for detection, to couple in the input you can use. And this is how it looks like in reality in the lab, which is actually just next to the poster session where you usually are. And what you see is the laser is up here, and then you have just some optical components which are connected by optical fibers, which are all these colorful strings here. And you can do that pretty fast. And that's one of the advantages of this system. So we're talking about here systems which we can modulate with signals which have 20 giga samples per second that you can input into this system. And you can detect with up to 80 giga samples per second the responses. And here you see one of our very early results that we achieved for this spoken digit recognition, the benchmark laser. So here would be more or less the threshold current of the laser. And the red and the blue curve show you the error rate of this recognition of the words. And we did that introducing the information electrically, but concentrate maybe on the blue curve here where we introduced the information all optically. And you see there's operating points like here, where the error rate of the recognition of the words is practically zero. It doesn't make any error in classification of the words after we train. And if you look, for example, for the speeds, so this was at 5 gigasamples per second. Meanwhile, we can do it with 20 gigasamples per second. You would here have nominally 300,000 words per second that you could classify, or meanwhile more than 1 million words that you could classify per second. That's 10 to the 5 more that you could do with an algorithm running on your PC. And we also already back then demonstrated this possibility to do different kinds of calculations at the same time because you use the same network. So we trained another classifier, another output node. Lest we get there a very small error, but there is a small error, but of the order of that we get it 99 out of 100 cases correct, also to recognize who spoke the word. So to sum that up, that part, so the recognition of spoken numbers was actually realized with practically zero errors. So we have a computer already which is precise to some extent, it's fast, or even very fast. And we made also a calculation how much energy did we actually consume in order to recognize a single digit. And it is a factor 200 lower than, for example, you would again require on a PC. So is that all? Well, I showed you also you can do parallel processing of other tasks. We could in principle, or we have even shown experimentally, that you can also but we can be much faster. We can do even standard arithmetic, so you can do in principle any kind of calculation. You can do matrix multiplication, vector multiplication, whatever, in principle, but it might not be the best system to do it, right? Because that's what the strength of the digital computers are. So you can, in general, classify patterns, images, whatever you want. And it's not restricted to this particular configuration. So we didn't have to tailor the nonlinearity of the semiconductor laser to do that, or that the optical fiber was important for that, or anything. This is, in general, such a robust scheme as a configuration that people have, meanwhile, been so fascinated by it that many different variants of it have been realized. So you see, for example, electronic implementations, optoelectronic implementations, hybrid optoelectronic and digital implementations, different kinds of all-optical configuration based on lasers or amplifiers or on coherently driven fiber cavities. This is exactly at the same level, but in principle it works for any of these configurations. And with most of them, you get high classification accuracy, reasonable prediction accuracy, high energy efficiency, high speed for some. But what I showed so far and what people have done mostly is benchmark tests. Certainly that's what you have to do because people will measure you by how good are you in benchmark as compared to other approaches. But can we really go towards real-world applications? And working with telecom hardware, certainly the obvious thing to try is choosing a real-world problem from optical communications. So can we use the same compensate for fiber propagation effects in Ethernet or long-haul communication networks? So what's the problem? The problem is that if you take Ethernet, which is typically at the moment at 25 gigabit per second, or long-haul optical communication, which is typically at 10 gigabit per second communication, that due to the propagation along the fiber, nonlinear effects in the fiber, as well as stochastic effects coming from the reamplification, lead to disturbances and distortions of the transmitted signal. But at the end, you still want to recover certain information. So for example, if you input a binary input sequence like this information into an optical fiber, and you propagate it, for example, here over 50 kilometers of single mode fiber for Ethernet, then that's what you get out. So by a simple comparator, you will not be able to retrieve the message. The question is, are you still able by pattern recognition to determine what was the original bit pattern? And can you extract the information again? Well, let's have a look into that. And here you see all the eye diagram of all the transmitted information. And you see it contains many different curves. Let's pick a few of them. Let's pick those which all correspond to a bit 1. Then you see the still corresponds to many, many different patterns, which are indistinguishable from many where there is, for example, a 0. If we, for example, say, okay, it seems that the previous and the subsequent bit also have an influence of what actually the pattern looks like. You see, if you take here a sequence of 1, 1, 1 in a row, you already restrict the patterns further. But even 3 bits are not sufficient. You still get different kinds of patterns. So how do we now do the pattern for a bit like this? We sample it with a certain number of samples. And now we mask this pattern, every sample of it, with one of these masks. We multiply it with it. We inject it into our system with delay, the laser with delayed feedback. We get the reservoir response state here. And we train the system with linear regression in order to train it to give us the correct bit. But we have to do it taking a certain length of the pattern. I just showed you in the beginning that a single bit pattern is not sufficiently long. The patterns depend on the previous and the subsequent bits. And here you see in the experiments the improvement that you get in bit error rate. So how many bits do you classify wrong from a certain amount of input bits? If you try to classify the pattern directly or using our reservoir computing approach, you get an improvement of 1 order of magnitude for transmission lengths of 50 kilometers. And in long haul, considering 3,000 kilometer transmission, we get still an improvement of at least a factor 3. So that's certainly quite important because that means you can, for example, extend the transmission range significantly. If we compare that to numerical simulations, we even see that there's more potential in it. So if we, for example, plot here the bit error rate against feedback strength and also the number of the bit patterns, the length of the bit patterns considered. So from the simulations for Ethernet, we expect at least an improvement of 2 orders of magnitude, and for long-haul communications, even up to 3 orders of magnitude. This is dramatic. Laser and some fiber components, we can realize photonic reservoir computing doing nonlinear prediction, pattern recognition, and even real-world applications, like post-processing of strongly distorted optical communication signal at very high rates. We're not yet there that we can do it in real time. So we still have some kind of speed penalty. We are, let's say, 1 to 2 orders of magnitudes too slow still. We still have to improve on the speed, although it's already pretty fast. But we think that can be overcome. So let me come finally to the point, what can we generally learn, more from a broader point of view. So, and I would like to, I call this a few myths debunked. So if you started from the original concept of reservoir computing and what was the recipes that were given, what of the recipe that was originally introduced were true, and which, for example, can we just by implementing it learn that they're not required? The first one is obvious. So while the recipe always told you, you have to choose a random network, you have to choose a random network, no way. No need for that. So there's actually even no advantage of random connectivity at all. Even people now studied real ring reservoirs with real nodes along a ring, and they find that they even have advantages, for example, like a random connectivity. So many networks, and that's why I said that in the beginning, in the end, many networks of dynamical systems, in principle, you could employ for doing information processing. What's the role of the nonlinearity? In order to be close to neural dynamics, people usually choose a sigmoid nonlinearity. It's like the kind of threshold nonlinearity, like the neuron which has a threshold in order to spike. Is that beneficial? Well, for most cases, not at all. So actually, choosing different kinds of nonlinearities in the experiments, Mackey glass nonlinearity, sine square nonlinearity, the more intricate laser nonlinearity, or quadratic nonlinearities, you can use all of those. And actually, in most cases, those work better than the sigmoid nonlinearity. So also that myth debunked. You don't need that. So it works very generally. This gets a provocative one. Does the reservoir have to really be nonlinear? There are some colleagues who even showed that the reservoir in principle can even be linear. In optics, they used superposition of linearly coupled optical nodes, if only the readout nodes are nonlinear. For example, intensity detectors, which is a square. Did we really need these random input connections into the network? Well, I don't want to go into details of all these different works, but to cut the long message short is not at all. There's different ways how you can determine the input connections, and sometimes you can even find these connectivities analytically, telling you, okay, this is, for example, the connectivity that gives you overall, in general, the largest variety of responses. What's the role of the reservoir size? So reservoir size means how many neurons or nodes do we have in the network? Is that the decisive point? Well, first of all, one nice aspect of the delay reservoir computing is the size can easily be scaled. All I have to choose in order to have more nodes in my reservoir, have a bigger reservoir, is taking a slightly longer fiber. Costs nothing. I don't need any additional components. But the essential point is, it's not the number of nodes which is really the decisive point, but what is essential is the dimension of the state space that I span. Not yet in the chaotic regime, but just below. Can we confirm that from the implementations of the systems? Not at all. Mostly, yes, we have been working in the stable regime. And you can work actually going close to the first Hopf bifurcation here, but actually not too close. But you can also go further away, and it still works nicely. And even we're now working on to see whether we can work in the autonomous dynamical regime, that you are within the dynamical regime. And why is that of interest? Because the concept assumes that if you don't drive your system with an input, you would always go back to a fixed point, to a stable state. Our brain never does that. If our brain goes to a stable state, it's dead. So it needs to be able to work in a context where you have a lot of dynamical activity and still we're capable already in a dynamical state in the first place. What about noise? Usually analog systems are discarded because they, oh yes, but then you're susceptible to noise. Yes, true. We are susceptible to noise. But the scheme is sufficiently robust to a reasonable extent of noise, reasonable amounts of noise. So you can get a good compromise between robustness and precision, or let's say a noise that you have in it. Because you do not want maybe necessarily always the highest amount of precision. Even in digital computing, people start to talk about approximate computing because, as shown in one of the first slides, precision costs a price. And the price is energy. So we have to see for every kind of computing, if we want to become more efficient, what precision do we need for a certain task in order to be efficient in terms of energy to do this task. That by choosing the implementation, we see that the concept can be drastically simplified. We see that many suitable coupling topologies work, a wealth of performing nonlinearities. We can do parallel processing. The technical implications I already discussed in detail. So what's the perspective for the future? Is this just something you saw? This was tabletop experiments in the lab. It only will be feasible if in the end you can go towards integration, right? And the system of the laser with feedback, for example, can be fully integrated in what is called a photonic integrated circuit. Here, this would be a photonic integrated circuit of 1 centimeter size or something. So you could implement all of that. And this guy would, for example, be capable of doing this data decoding in optical communication, probably even without any speed penalty. If you think that, for example, you have to mimic, if you want to extend the concept, that you want to mimic the brain more and want even to have something like action potentials, there's beautiful works by people like Sylvain Barbet's group in Paris, which show that a semiconductor laser, in this case a circuit, you can even go to spatial networks of multiple nodes. And this is, for example, what you see here is in total maybe 2 by 2 millimeters. Is an array which contains, in the end, 64 lasers which emit in a square pattern here out of the surface of the chip. And we realized a network of these lasers that then we can use to do reservoir computing, and we're at the moment trying to scale that to larger numbers of lasers. And that's what, for example, Moritz, who's sitting over there, will be doing in his PhD thesis. That this is a growing field is really, you can notice that the number of meetings dedicated to it is growing year by year. So more and more people are getting interested in this kind of analog computing, more and more from different platforms, not only optics. There's even people trying to implement reservoir computing in mechanical oscillators or in with alternative concepts of computing along these lines of thought. So to sum up, to finalize, so will future computers be optical after I have been so enthusiastic about it? Well, maybe, but maybe also not. We know that certainly many predictions in the past were wrong because the evolution or development of another concept was just overpowering all the others. We'll see. But photonics will definitely play an increasing role in what people call it, if you talk, for example, the decoding of the signals, people might call optical accelerators, or specialized solutions first to start with. Or more and more parts becoming parts of smart communication and sensing infrastructures. Photonic information processing might also help reduce communication data and processing already into the network and reduce the amount of energy and data required, and also, to some extent, democratizing computing, going away that all the artificial intelligence is based in the super cluster computers and centers of a few handful of companies which dominate then the market. And even we see that, that companies are starting to jump on the topic, even in Silicon Valley. But certainly one key problem that we will have to solve, and which is one of the major challenges for the future, is I showed you more or less a bottom-up approach with an initial, let's say, basic cell of computing you can start with. But one of the key questions will be scalability. How do you scale that up to become a concept that you can scale, like, for example, you could scale the von Neumann machine. So for me, at least, the bottom line of all this is reading all those who have a significant contribution to all the things that I've been showing. Those are people with whom we have been working here in Palma, in IFISC, Leonard Appeltan, Julian Bueno, Apostolos Aguirres, they're both just at the conference at the moment, Daniel Brunner, who's now a CNRS researcher in Besançon, Miguel Soriano, where is he? There he is. Xavi Porte, Neos Oliver, Konstantin Hickes, Sylvia Ortin. Where? Over there. Claudio. And some colleagues from other institutions, Laurent Lager in France, Guy van der Zande, Jan Dankert in Brussels, and then Gostia from Duke University in the US. Thank you for your attention.
Ingo, when working below the application of the error is very low, what happens when you go beyond? Do you have a regime in which the error is set at still good? How much?
No, usually if you do that, the performance goes down drastically. Yeah, and the reason is that then the response will become dependent on the dynamical state of the system at that time. But what we've been doing with NEOS is investigating, are there not particular conditions such that you can be in the dynamical regime, but nevertheless the responses are showed that this is possible. But you have to fulfill some conditions for that. If you just do it with any kind of dynamical system and you go beyond the first bifurcations, your performance will drop. And certainly I think also that you might not get the same performance than with a fixed point. But as I said, being able to be robust against, for example, some dynamical activity, even if the performance is slightly lower, would be a very interesting aspect. And it would also help in the direction of understanding how does actually our brain do it. Because in the end, I didn't mention that at all. One of the major motivations certainly behind all this is that they, for example, at the moment are capable of simulating 10 to the 6 neurons, which is still small as compared to the 10 to 11 neurons that we have in our brain. And these machines need kilowatts of power. Scale that up to 10 to the 11 neurons. Our brain does all that with 10 to 25 watts. So we know it works. We have it here. We have the evidence here. We only need to understand it. And we know it works with noise. We have a lot of chatter in the brain. We know it works while it is dynamically active. But we have not figured out at all yet how the heck we really are capable.
You have shown that there is no need for a random network. There is no need for working at the threshold. You don't need nonlinear. So but have you learned something on what is the right recipe? So it's you discovering really what is better than the other, or you simply have just disconnect the pieces of the experiments.
You detect certainly a weak spot. Well, what I introduced is that there are a few necessary conditions. For example, consistency is very, very important. We know that. We know that you need to be able to span a high-dimensional state space. But for example, there's a lot of knowledge still lacking that it will be able to solve it. Those are so far estimates from experience. So there's a lot of things that need to be learned. So what I showed you, and you certainly recognize that, I only, let's say, dropped a few requirements as they were originally considered. But we do not certainly know yet completely what is the definition of a system that is not only the necessary conditions, but sufficient conditions, minimal set of conditions that are sufficient that you will get a performing computing system.
Have you tried sparse representations? Would that help?
Interesting point. This could be very interesting, but to be honest, at least in this area, no one has tried it yet. So sparse representations, even compressive sensing, if you think of sensor networks, very interesting aspect, something for the future, but we haven't tried.
If I tried, how long would it take me to publish a paper on that?
I don't know. As you know, having really new revolutionary ideas will always take you long to publish.
Yeah.
Because even more you have to convince not only the editors but also the peers that this is something interesting, because everyone will be dubious if it's not something they really know already.
I may not want to go to more computer, run a program, and then, so you did mention the arithmetics as one of the possibilities of logical
Yeah.
operation, basically.
It's not its
Can
strength.
you get an error-free logical operation there? Otherwise, you cannot compete with
Well,
other computers doing that sort of tasks.
Let me put it differently. So we get a finite resolution in the computing by the noise. So that's what we get, for example. For example, in our case, we found that we were still signal-to-noise limited, that the resolution of the calculation was 4 to 5 bits. Yeah? And that was limiting then the precision. It's not necessarily an error. It's, let's say, it's a resolution that you get. But what you say in principle, you say, okay, you want to go to the computer, and you want to be sure it gives you the right answer. Well, that also means or shows how much you have been certainly growing up always within the von Neumann machine. But you also have been growing up with yourself. And we know we do fantastic things, but we also do mistakes. But that is not necessarily depending on what task you are. In principle, you can get logical gates error-free. Logical gates have been demonstrated. I don't know yet now from the experimental side. That depends a little bit on the tuning. I'm sure it would in principle be possible. But the question is that a smart thing to do? Because this is not a computer with which you want to replace the logical gate of von Neumann architecture of conventional computing. You deliberately want to go towards tasks where usually for the von Neumann machine is weak and where the human brain is strong. So it's not to replace the von Neumann machine, it's rather to complement it for the kind of task where standard computers are usually weak. It has similarities with the support vector machine approach in the sense that you also use the mapping onto the high-dimensional state space, only that in support vector machines for the experts you would only use the few examples which are close to the boundaries between the separation, and here you use all of them. But there are similarities between the concepts, yes. So in the end, but we go also in different aspects beyond it. So we're certainly inspired by these, but you also see that we use really dynamical systems. These networks, usually these neural networks, are not dynamic kind. And trying also to take benefit from that, it's really a dynamical system that we're using here. And that allows you, for example, to use the systems more bandwidth efficient. You can really use them in a domain where you get nonlinear transients, while in nonlinear mapping, you would need to have much higher bandwidth than you can actually use. So we try to really come in from, as I said in the beginning, taking really ingredients from all these different areas: machine learning, neural information processing, dynamical systems.